This is Wes Weimer here with a third video guide for Programming Assignment 1, the Rosetta Stone. This one covers implementing depth-first search in COOL, the classroom object-oriented language. We'll definitely cover COOL in class, in lectures, and a COOL reference manual is available online. But one of the most important things to understand about the language is that it was designed to make it easy for you to write the interpreter. And we did this by removing convenience features that aren't necessary for Turing completeness. So in COOL, you don't have as many convenient data types, you don't have the nice syntax you might be expecting. So it's harder to write programs, but easier to interpret them. So in Python, a lot of our jousting was with testing or finding the right function. In OCaml, we spent a lot of time trying to get past the type system to make sure we were writing the right program. In COOL, we're going to spend a lot of time being frustrated at the language because it's just hard to get anything done with so few abstract data types. It's not impossible. COOL is Turing complete, but you typically don't actually want to create a Turing machine simulator in order to just find the shortest path. And that's one of the reasons that we're just going to do depth-first search in COOL instead of shortest path. Even just depth-first search is going to be enough of an adventure. So, once again, we're in our, we've unzipped the Programming Assignment 1 hints. And we do have one of them that involves COOL, unsorting in COOL. And I'm going to copy this to depth-first search in COOL, because we remain bad at naming. Pull it up, and again, the syntax of COOL we will cover in class, and we also cover in the COOL reference manual. But a COOL program is a series of classes. If you ever want to call the equivalent of printf, you need to inherit from IO. Main is a privileged class with a main method. And if we are going to have a little comment here at the top, Wesley Weimer, WRW6Y, read in a graph from standard input, note vertices and edges, maybe just edges, all right? And then can we DFS or breadth first search? I actually don't care. Can we reach from some start node to an end node? This is our plan. And every data structure we want in COOL, we have to build out of the primordial ooze of basic types. So if we look down this unsort COOL program that's provided, you notice even the lowly list is not built into COOL, much less Python's favorite hash map or OCaml's hash table. We don't even have lists unless we do them ourselves. Class list inherits IO. And the way we typically do this in COOL, this class list, this is like an abstract parent type. We'll never actually make a list itself. We'll either make an empty list, nil, or we'll make a list with one element that points to another, like either a list cell or a null pointer. And this is more like a, an abstract specification that they both adhere to. So we've got list. Cons, this terminology comes from scheme, but cons means a non-empty list cell. Car and cdr, this is the contents of the list, and cdr is the pointer to the next element. You have a number of cons cells, and then eventually at the end of the day, we have nil, which is the empty list. All right? So conceptually, something like the list 1, 2, 3 would be like cons of 1 and cons of 2 and cons of 3 on nil, right? In COOL. That's how we build up the list out of object-oriented constructors. All right. But in COOL's type system, which does have static dispatch and dynamic dispatch and all that stuff coming out the wazoo, this list that we have so far can only hold strings. And that's good in some sense, because we will definitely need to hold a list of strings. But we will also want to hold a list of string-string pairs. So we're going to need some key data structures All right? We have to build each one in cool. And one of them is we want a list of string. And the place where we will use this is list of visited nodes. If we want to do DFS or BFS correctly, we can't loop forever if there's a cycle in the graph. So we have to keep track of where we've been before. So this means that we will need to be able to add a node to the list of visited nodes. And we will also need to be able to check membership. Right? Have we been here before? But, right, now we could also use this instead of visited nodes. This could just be list of all nodes in the graph as well. If we have a list of strings, we can do all of those. We will also want a list of string-string pairs, and this will be the list of edges. Or if we like, the list of, oh my gosh, list of remaining edges, because sometimes we'll want to sort of iterate over all of the edges. Right? And this is a trick in cool where, you know, when you sort of don't even really have a for loop. If you want to iterate over a construct, consider all of the strings in a list, you have to do that by adding methods to list classes. You can't really do it from main. You have to do it inside list. So your usual depth first search code would be something like this. And we do it in, you know, kind of Python or whatnot, where you know where I am now. This is like, you know, my current node, my destination node. I have all of the edges, and I have where I've been, or something like that. And if current is in visited, then you're done, or whatever. But otherwise, right, you want to essentially find, you know, for every current new node in all of the edges, this isn't really how you'd write it in Python, but you sort of get the theory, then you would kind of call yourself recursively, right, on, now we're in the new node, we have the same destination, the same edges, but now there's this new visited, which is current plus the old visited. Right? Right. If current is in visited, we return false. And I guess the other condition here is that if current exactly equals our desired destination, then we return true. And again, this is just pseudocode, and we don't care about this sort of double equals versus normal equals. All right. So we would like to write this sort of DFS or BFS procedure, but we can't directly because there's no way to write this for loop. There's no way to iterate over all of the things in edges very easily, not necessarily. So one of the ways that you often end up doing this in cool is embedding it in a class like this. So one of the other things we'll need later on, right, this for loop, we want to sort of go over all of these edges. We will need some sort of do DFS over this list of edges method. All right, we'll comment all of those out for now. So let's go check and see, does our list of strings currently have adding nodes and checking membership and that sort of thing? All right. Well, it definitely has adding nodes. It has some other way to add nodes, calling insert, which sorts them in reverse order and we don't care as much about. But it does not have a way to check membership. So let's add a contains function. I'm going to add a contains function that takes some element x, which is a string, and returns a Boolean. But remember that list itself, it's like an abstract data type. You should never, call this. What we'll really want to do is implement it for cons and nil. Right? So here we are in cons. Well, you contain the string, right? If the string they care about is exactly the string that you have, then you can return true. Otherwise, you should call yourself recursively. Maybe the next person in the list has it. In cool, if ends with phi, because why not? Because it makes parsing easier. There's no, the dangling else problem is less of an issue because every if matches up with a phi. Right? And then by contrast, if you have the nil or the empty list doesn't contain anything by definition. Right? So again, we want to sort of test early and often. We've added this contains function. Let's see if we can even get past the cool type checker. All right, now remember currently this unsorts the list, so I put in hello world and it said world hello, but we passed the cool type checker with our new contains function. Right. Now let's go back up to main and make sure that we're reading in everything correctly. Right? One of the first things we'll have to do is read in the graph. So in the main object, we call the main method, and we start out with this list, and it starts out being nil, and then while we're not done, we read a string from the input. Cool's error handling, cool doesn't use exceptions because if it did, you would have to implement them later, so we're saving you effort. So it returns the empty string if you've reached the end of the file or if things are going badly. So we're done reading lines, at which point we're done. Otherwise, we insert this string into the list. Just like if ended with phi, while loop ends with pool. Pool is the opposite of loop, spelled backwards, right? And then at the end of the day, we print the list. So we might consider, we'll just add in something here, right? What if L contains hello, then outstring contains hello, else outstring does not contain hello, phi. And let's see if we can check this out, try out our contains function. Does cool still work? A, B, C. And we see it does not contain hello. A, B, let's sneak it in. Hello, C, D. Contains hello. All right, so it looks like our membership function for lists is working as we expected. So the next thing we'll have to do is add a list of string-string pairs. And we will need to essentially copy all three of our list classes. Well, need is very strong, but this is the way I'm going to show you how to do it. So we're going to copy list all the way down to the bottom and make, right, this pair of strings list, which I will abbreviate using a different acronym in real time. We'll call this the string list. And it inherits from IO. And when you add something to it, right, now there's going to be not just a single string, but you'll pass in two strings. Okay. Just like we have our string list, we're also going to have string concells, because normal concells just hold one list, but we need to hold two. So we make our string concel, and we will initialize it with A and B and self. Right? You can insert. Actually, this insert function was to insert things in a sorted order, which we don't even need. You can print, which we definitely want. Contains, we don't immediately need. We're going to need to add this DFS function later, which is going to be really obnoxious, but we don't necessarily need contains. So now, let's make that SS concel that we promised. And before, we had a single car and a single cooter. And just to keep with the same naming, let's now say that we have two fields, A and B. And so A is the contents of the left tuple part, and this is the right tuple part. All right. We don't need this contains function, but you do get to initialize us with two strings, A and B. And now, the A field, the XA field gets A, and the XB field gets B. All right. Insert, we don't care about, but print list now does become different. and we print out XA, and then we'll print out the comma. And in fact, to make it, look like a list or something like that, like an ordered pair, we'll use this fun syntax here. And then after that, you have the other comma, and then we will close it off. So we're going to print out ordered pairs. Oh, and we want to print out A and then B. Otherwise, we will feel badly about ourselves. All right. In addition to the cons cell, there's also the nil cell. Oh, this isn't going to work. Up here, we said we were returning cons. We're totally returning string cons. And string cons doesn't inherit list. It inherits string list, and its tail pointer is string list. This is why it's so obnoxious to have types in cool. So obnoxious. I'm going to go back in a bit and show you. It would yell at us if we got any of those wrong, but rather get them right the first time. All right, so now we've got string nil, which inherits string list. Don't care about insert. Print remains the same. Don't care about contains. First, let's see if it even compiles. Yeah. On line 140, type check. All right. So we believe we are calling sscons is, and then we call new cell.init. Init takes A, which is a string, B, which is a string, and a tail, and returns itself, which is an sscons. So what is it complaining about again? Let's just make sure. Argument 3, SS list does not conform to formal type list. They're so right. Here's argument 3 where we're passing in self. But if you look at the init function, we forgot the SS in argument 3. All right, you win this round, cool. Aha. AB, hello, CD, and it says contains hello. All right, so now we have these lists of pairs of strings, but we never actually populate the list. So now let's do that up here. When we're reading in input, let's read in A and B. Right? And if we're done, if either the first one or the second one returns the empty string, but if the first one doesn't work, the second one's also not going to work, so I'm going to be cheap and just check the second one. Right? But now instead of a list, we want a string list, and we're going to call it string nil. And indeed, I'm not even going to call it I'm not going to call it L. I'm going to call it edges. Haha. If so, then edges gets, well, edges does not have this convenient insert function, right? But it does have cons. All right. So edges gets edges cons of A and B. See if that works. All right. Now we don't get to do this contain stuff anymore, but we should be able to print out edges. Now we have a number of graphs lying around, like this simple graph, but they all have these edge weights in the middle, which we are not going to deal with in cool. So let's consider this very simple graph that just has two edges, A goes to B and B goes to C. Let's see if we can make that work in cool. A goes to B, B goes to C. All right. And when I eventually figure out how to exit the input, we see those edges in reverse order because we cons them on at the front, or like this, right? Now notice, by the way, that once again we have this issue related to white space at the end of strings. And for cool, or for this particular maneuver, we're actually just going to remove that from the file rather than trying to deal with it in cool. More on that story later, by which I mean we are never returning to that story. All right, so we read in our list of edges. This is our implicit graph representation. And now what we want to do is search through and see if it is possible to reach one node from another, and if so, return the path that we took to get there. All right, so this is our DFS maneuver. All right. And again, this for loop, implicitly, we are going to implement this for loop by distributing this functionality over the SSList class. Just like we did to check and see if something is present. You know, we wrote a method that called itself recursively and the nil case returned false. We're going to do the same thing here with DFS. So one of the first things we'll do is make like an interface for it, even though we won't implement it here. So we'll have our current node, which is a string, and our destination node, which is a string, and our edges, which are going to be a string list, and our visited set, which is just a list. And if this succeeds, then we will return a list of nodes in order, so a list of strings, right? And we'd like to say, well, you can't actually do it, so we'll just abort. But interestingly enough, cool is not going to like this because abort probably does not conform to type list. Let's see what cool thinks about that. Uh-oh. Abort returns an object, but you need to return something that returns a list. So, again, you're never actually supposed to call it on SSList. This is like an abstract class that never occurs. We will instead return a new empty SSList. SSList does not conform to list. They're so right. We don't return a list of edges. We return a list of nodes we took to get there. All right, so now that works. So that part was easy. This was like the .h file, or like the Java interface file. Right? But now we need to add it to our const cell and our nil cell. Let's add it to the nil cell first. Right? If you're trying to do breadth first search or depth first search or something like that, and you've gotten down to the point where there are no edges left, you didn't make it. It didn't work. Right? So we will just return nil, the empty list. What steps did we take to get there? We took no steps. It didn't work. However, for our actual ssconst cell, this is where we do have to do all of the work. And also where we get to joust with a bit of cool syntax. You may have noticed that a lot of cool functions start with this extra curly brace kind of maneuver. And that is that unless you put in these extra curly braces, every cool function is one expression long. So if you want to do multiple bits, you need to make your own block. All right, so one of the, how are we going to do this? Well, self, conceptually, self is a list of edges, right? We still have to try, right? That remain for us in this recursive procedure. But we can only transition on an edge if XA matches current, right? Now, this may sound a little confusing, but let's say that this is our edge list, right? A goes to B, B goes to C, let's say B also goes to D, and D goes to E, right? And we're trying to do DFS where current is B, right? So we'll get called on this whole list, right? And the first time we say, oh, well, this edge A to B, we're not there, so we can't use it, so skip it and call yourself recursively. All right, we can totally do this, right? So this is going to be skip, A to B, do nothing. When we see B to C, we then call recursively on, and now current is C, right? When we see B to D, we call recursively, but now the current node is E. And when we see D to E, we skip that. There's nothing to do there. It doesn't apply to us. And as soon as one of these recursive calls succeeds, we win. It was reachable. We found it and we got there. All right? So that's the sort of the highlight of this recursion. But we have to do these two sort of sanity check safety cases first. All right? So the first one is if current is equal to the destination, right? Then we win. We got there. This is good. It is reachable. and we need to return the path we took to get there. Which nodes did we visit? Well, by construction, we're actually going to have those in this list visited. We just need to add on the current list, or the current element that we're in. So we'll want to return visited, but add on the current node, which is also the destination node. Every cool if ends with a cool phi. If current is equal to destination, that's sort of like the positive case. There is also the negative case. If visited contains current, right? Then we didn't get there. And I think we've said so far that didn't get there, we were returning nil. Note this nested if structure. Here is where we do the real recursive deal. And we'll even just move this comment in and shift it over a bit. All right, so we need to figure out if we're in this skip case or if we're in this case where we can actually take the edge. All right. And for something like B to C, let's say C never actually reaches the end. Like let's say that source is A and dest is E. Well, even though B can transition to C, that's a red herring. That's not going to get us there because C is a dead end. Right? So we need to both call ourselves recursively with current is C, but also call ourselves recursively on this executor. Right? Don't forget executor recursive call. All right. So, with that in mind, right, how are we going to structure it so that, sort of as soon as one of these succeeds, we're done with it, but otherwise we're not? Well, in cool, basically, we're just going to have to write it out longhand. So the first check is, does current match XA? All right. If current does match XA, then one of the things we want to do is call ourselves recursively. All right. With current equal to XB. We'll want to check and see if that succeeds. Here's our recursive call result, which is going to be a list of nodes. Okay. It is equal to the result of a recursive call. Right. We want to call depth first search. We've been iterating here through all of the edges that sort of remain outgoing on this node. When we transition, we get all of the edges again and call ourselves recursively on all of the edges. The current node is now XB. The destination stays the same. All of the edges are still the edges. Oh, but the visited, we would need to update visited, right? Which is going to be just like visited, but we cons in the node we're currently in. But that's not cool syntax. Maybe that's cool syntax. Uh-oh, but now we have like a bunch of stuff going on, so maybe we want a block just in case. All right, and we're going to call ourselves with this new visited. All right, and then if the recursive call result was not nil, then things are good and we should return them. Otherwise, we need to keep going down the list and do this don't forget maneuver. How do we check and see if something is nil? Oh, we forgot to give ourselves that power. And cool is so weak that we don't have it unless we give it to ourselves. So back up here with list of strings, we also want check is empty. All right, so over here in list, is empty, returns a bool. You should never call it on list. Any cons is not empty by construction, right? And any nil, nil is empty by construction, cons is not empty by construction. There is also a way to do this in cool using the case expression. We're going to avoid the case expression to make this video a little easier. All right, so where were we? We were writing the world's most complicated depth-first search procedure. We'd done a recursive call on the result of this edge, right? If the recursive call result is empty, then don't forget, try the other recursive call. All right. Then we do xcodr.dfs, where current is unchanged, dest is unchanged, the list of all edges is unchanged, and visited is new visited. Otherwise, we won with the recursive call result, so we can just change that. We can just call that. All right, that seems pretty good. If current is not XA, then we just want to do this, which means that we want to pull new visited up here. Since we have this curly brace maneuver, every actual statement here needs to end with a semicolon. All right. So, is there any hope of the cool compiler liking this the first time? Let's see what it has to say. Line 203, syntax error near close parenthesis. Here's line 2. Oh, we were right there. All right. When we have one of these curly brace things, every statement needs to end, every statement inside at that level needs to end with a semicolon. Type check. Unbound identifier recursive call result on line 185. So we let, oh, recursive, like if you swear multiple times, recursive call result, you will with cool. Let's try this again. Ho ho. All right, so we've implemented what may be a depth-first search procedure, but we never actually call it. So let's go all the way back to main, and instead of checking to see if something says hello, all right, we're going to do, we're going to try to get a path from A to C, where A is where we start, C is where we'd like to go, and then we've got edges and visited. Edges is all of these edges, but visited is currently a new nil. We haven't visited anything yet, right? And we print out the edges. I mean, that's all good. But then we'd also like to print out the path. All right. The moment of truth. All right. Well, we don't actually see. We'll just have a little outstring before path. After path, just to make sure we're getting there. Unbound identifier path. Once we do this, we need, once again, the curly braces, because the let in takes a single expression. So if you want to do more than one thing, you must have curly braces and semicolons. All right, so before the path, after the path, so we're getting the empty path, which was what we returned if we couldn't find it. So this is its way of telling us, oh, I couldn't quite get from A to C. Let's see if we can get from A to A. All right, that worked. So let's see if we can get from A to B. That part isn't quite working. So let's go through and see where we can find our conceptual mistake. We know, let's just re-verify, there is an A to B edge. All right? And indeed, it's the second one in the list. So let's go back down to SS list. And we're going to go into DFS, and the first time we get here, right? All right, let's just add in some printf debugging. Printf debugging in cool, it's not pretty because it does not have printf. All right. So when we call ourselves on A and B, and that's we call ourselves with sources A, which is here, and we also call ourselves presumably this second time. When we're doing this printf debugging, let's just note what XA is. And just print those out, and then have a little new line. Dig this printf debugging. Out string. Notice the capital S, because I did not. All right. So we first are doing our depth first search, and we're looking at an edge that goes from B to C. So we skip it, which is good, and we call ourselves recursively, and we get to a time when XA is A and XB is B, and that looks pretty good. So now let's go back to dfs.cl and see where we get in these if statements. Cool printf debugging is, you know, right up there with like root canal surgery. So if visited contains current, well, why don't we let's see what visited is. I think it was called something like print list. Not OCaml. Cool. I wish. It is called something like print list, but it doesn't print its own new line. So that was hard to read. So let's try it again. Right? In our first recursive call, we haven't visited anything, and that's good. And in our second recursive call, we have visited A. Right? So here's the logical mistake. We haven't actually been through A yet. Down here, where we're calling ourselves recursively on xcooter, we don't want to use new visited. We want to use just visited, I believe. Let's try that out and see how it goes. Now when we're trying to get from A to B, our path is, well, we con, so the path is in the reverse order, AB. Let's see what happens when in cool we try to get from A to C. We seem to have found ABC. But once again, this test case, and it doesn't fill me with a whole lot of confidence. Let's see if we can go back to one of those awesome graphs we had lying around. So we had this web graph, right? And let's make our simple web graph where we're going to remove all the weights. All right. Remember, we're not asking for the shortest path. We're just asking for any path from A to C. Actually, before we run that, is there a way to get from A to C? No, not in this graph. There's no way to get from A to C. So hopefully we'll get the empty result. And we did. There was no path. This was the empty result. But for this program, we're really supposed to go from S to E. Let's just double check. S to E. Love it. So now let's rerun cool. And now it says we can get there S, C, D, E. Does that work? S, C, D, E. Whew, that works. But remember, whenever we wanted to, really test our soul with this, we remove the CD edge to make a tougher test case. So SA, SC, CA, AB. Here's the CD edge that we're removing. We removed the CD edge. All right. So now let's see if you can still get there. and it says SCABE. SCABE. I mean, sometimes you take the long way home. There's no reason to go to C. They could have done SABE. But this is not Dijkstra's algorithm. This is any reachability. SCABE is a perfectly fine answer for can you get from S to E. All right, so we've written a cool program that operates on a graph. And just going back up to the top, right? You're writing a cool program like this. The things to keep in mind. Well, some of it is relatively syntax directed or low level, like what's up with the the semicolons inside the curly braces, and that's super annoying. Right? But the other bit is that for every data structure you want, you have to build it yourself. So if you want, these are like notes for you. If you want a set, all right, then you code in cool a list plus the contains function. Right? Officially, you do a set out of balanced. You do not want to do balanced trees in cool, right? You do not. If you want, like a mapping, right, from A to B, then you do a list of tuples AB plus, contains function that takes those two arguments, right? Or possibly returns a list or something like that. If you want an AB set, you do a list of tuples AB. Basically, every data structure you want, like you want an array, you do a list, right? You want a hash table, you do a list. List is pretty much it. You might at some point, like if you, here's one. If you want a matrix, you do a list of lists. So the car, the head of the list, points to another list rather than pointing to a string or containing a tuple. So the basic list is the standard recursive data type, and it's sufficient for Turing completeness. But you just have to get in this mindset of for every data structure you want that would just be built into some other language, you want to think about the minimal set of things you need, all right? And then you have to code them all up. Now, I mentioned earlier that we didn't really need this isEmpty check because we could have used the mysterious, essentially like instance of operator in cool, which would allow us to see if it's an instance of null or an instance of cons. Let's say that we've forgotten how that works. It's not much of a stretch. So we'll want to go back to the course webpage and go over to the cool reference manual and look up the so-called case expression. A case expression has the form blah, blah, blah. All right, so we're going to go back to that place where we had isEmpty, and we're going to get rid of isEmpty. And instead detect, all right, so here we've got this call to isEmpty, all right? Instead, we're going to check what the type of recursive call result is. So we've got type recursive call result. And we just take a look. How does this work? We say case of, and then the ending for case is esac, just like the ending for loop was pool. It makes sense in a like demented sort of way. All right, so we've got this identifier binds to type is an expression. What the case expression in cool is supposed to remind you of is match with in OCaml, right, or something similar in Haskell. So what we want to do is something like match recursive call result with, if it's like x, which is nil, then you have you call code A, and if it's y, which is a cons, then you call code B. Like this is what we're trying for, but it's not going to look that pretty because it's going to be in cool. So if we have x, which is, the recursive call result, would be list. This corresponds to it being empty. So we do this thing, and if it's instead y, which is a cons, then we can just return the recursive call result, which is also y, which is bound here. And if it's z, which is an object, then that should never happen. So we will abort, which actually cool will, well, it will even abort at runtime if there's some sort of problem. All right. And maybe after this ESAC, we need a semicolon because it's inside curly braces, so why not? Let's see if we've implemented this case correctly. Parse error near y. All right, well, let's go back to how this syntax is supposed to go. Oh, there's a semicolon here written explicitly. So I guess we need a semicolon at the end of each one of those. SCABE, I believe that was the answer we were trying to get. SCABE for, yeah, that was the graph where we'd remove that edge. So we're getting all the same answers we got before. SCDE for the full graph. SCDE, yeah, that totally works. But we removed this isEmpty function. If this OCaml analogy doesn't work as well for you, this is kind of like if recursive call result is an instance of nil, then do thing one. Else if recursive call result is an instance of cons, then. So this case, it's like a series of if then else's where we check instance of for each of these types. All right? If for some reason you need it, this new variable is bound to the appropriate type. So we could get the same thing by returning y here, because recursive call result is y. It's just that the type system knows y has type cons. Let's just try that out. Case error near ESAC because I forgot the semicolon, which is required. All right, so it gets the same answers as before. So we did not have to do isEmpty. There is a way to dynamically check the types of cool expressions. This is like a null pointer check or an instance of check that we've done here. All right. So notes for you, if you want anything, use a list. All right. And then think of what functions you need to support on it. We really wanted to do something like for every pair in edges. But if you think about trying to do this, it becomes a little awkward. Edges is a list, and if your code was in main, you'd somehow, like, oh, I want to get the list of all of the things in edges and go over them. It sort of reduces to the same problem. Like, I don't know how to see the contents of a list. So when you want to look inside a data structure in cool, you typically have to add that function to the class in question that implements the data structure. If you want to check membership, right, you put that inside the list class. If you want to have a DFS loop over all of the edges, you can put that inside the list class. This isn't the only way to do it, but it's good practice for thinking about things in this manner for cool, abstraction through object-oriented programming. And at the end of this, we'll just walk through, brief reminder about what all of these lines are doing. Main, you need one in a cool program. Inherits IO, you need that if you want to be calling print. Right? Main is a special method that's always called. In let, this time we have a let. You can declare multiple variables at once. Later on, I use two let statements. I never remember the syntax for this, like this comma. Rather than having the compiler yell at me, I just don't use it. So edges is a string list. We have to give everything an initializer. Otherwise, potentially it starts off at void. Don't do that. New SS nil, and then whether we're done or not starts at false. In cool, all variables are mutable by default. You can just have assignment statements, so it's not like OCaml or Haskell. While we're not done, we read in string A and string B. If there's any sort of problem, one of these will be the empty string, at which point we are done. Otherwise, we cons on to our edges that an edge from A to B also exists. We print the edges for convenience, and then we do depth first search on the edges, trying to go from S to E. And we currently haven't visited anything yet. We use list to keep track of sets of strings, like our visited set. So cons just takes a single new string. This is like an abstract type, so we never actually call these. Everything in the program would either be a cons or a nil. Okay. Xcar, car is the fancy Lisp name for the data in a list. Here's our membership check. If we have exactly the data you want, we return true. Otherwise, maybe somebody down the list has it. To initialize a list, this is like a constructor. Right? If you have a head and a tail, we assign those, and then we return ourselves just in case you need it. This insert function is vestigial. We're not using it. It's in the unsort. We just didn't bother to remove it. And then here's print list. And then nil. To insert something into nil, you just return the single element list, so that's pretty easy. Print list does nothing on the empty list, and the empty list contains nothing. And then the real action was here in this list containing tuples, this string list. Once again, this is like an abstract type definition. We don't expect to call any of those. But here, cons is a non-empty list cell with two parts, A and B. You could have like as many fields here as you wanted, right? But we're just doing A and B, which are strings, and then a pointer to another list, possibly nil. We have our relatively complicated depth first search recursive procedure, where self is remaining edges to consider, current is where we are, dest is where we want to stop, edges is all edges in the graph, visited is where we have been in this path. Note the difference between self and edges. They start out the same. They start out, all of the edges are available to us. But the point of this recursive call is to sort of do a for loop over them. So self gets smaller as we walk down the list making recursive calls, but we save a copy of the full thing because when we transition to a new node, we want to start again going over all of the edges. Right. Here's our debugging printing. We could have done some string concatenation to make this look better, but it's typically not worth it. Here are the base cases for our recursion. If current is dest, good, we win, and we return everything we visited plus we ended on this node. Otherwise, if we would be in a cycle, we stop because we want it to be an algorithm and not a semi-algorithm. And then here's the real trick for recursion. Self is a list of edges we still have to try. Just to make this clear, self is a subset of edges. I can't spell in English, right? And we simulate the for loop by having essentially like self gets self.next over and over again. That's the recursive call. So we make our new visited set if we need it. If current is, if we are currently in a node that is the source of this edge, then we can follow this edge and keep going. So we make this recursive call. If that recursive call succeeded, we win. Otherwise, we keep going down the list of edges without, taking that one. And that code is duplicated over here. We keep going down the list of edges. This part where we call, xcurter.dfs, this sort of corresponds to it's like the spiritual equivalent of self is self.next is the xcurter.dfs. That's our comment from before. Initialization, the pseudo constructor just takes 2 arguments now. And then ss nil, there's nothing to do when we're printing. And if you're trying to depth first search in a graph with no edges, then you fail. All right, that's it for cool. Again, we will be covering cool explicitly in class, but part of the required assignment is for you to try out a new language like this.